Okay, now let us look at the question of the quality of solution that we get. Remember, we are doing numerical analysis here. So we are A in our case is kind of a stiffness measure. B is a set of force vectors. So a legitimate question to ask is, if, for example, we make an error of say delta A in A and an error of delta B in B, how much of an error will that translate to in X? So if I have a slightly erroneous A, which is A tilde, and slightly erroneous B, B tilde, I would expect that the new solution X tilde will only be slightly different from the actual solution X. Is that the case? Will delta X be always small? Now, we will answer this question or answer this question without elaborate proofs, but to answer this question, we need to know how to measure the nearness of vectors and matrices. For example, when we say X tilde is slightly different from X, or A tilde is slightly different from A, what exactly do we mean? How do we measure this nearness or farness of quantities which are not just numbers, which are a set of vectors? So to answer the question of whether a small perturbation in A will and a small perturbation in B will cause a small perturbation in X, to answer this question, we will have to find ways of quantifying in some ways vectors and matrices. So to do that, the first um, idea that we need to learn is that of a norm of a vector. So we are dealing with things like displacements or vectors of degrees of freedom, which is what X is, and this is n-dimensional. So if we have a n cross n system, then this is an n cross 1 vector, this is an n cross 1 vector, and we assume that all n cross 1 vectors live in this space Kn, the n denoting the dimension, and its components are x1, x2 to xn, and the basis vectors are ei, so that you can write x as xi ei in terms of the components and the basis. Now, to quantify this vector, we can define a mapping, which we call a norm, that takes this vector as an input, this vector as an input, and gives me a scalar that is indicative of the size of the vector or the quantification of the vector. This has to satisfy some rules. For example, this norm should be 0 only when x is identically equal to 0, otherwise not. It should, if you multiply all elements of x with alpha, then it should increase by just alpha. Then there's this triangle inequality, not very important for us, but these are general definitions, general rules that any kind of norm of vector must satisfy. Now, the vector space Kn and the norm together forms a normed vector space. But the definition of a norm, the way we quantify a vector, is not unique. The choice is not unique. Many norms would satisfy these three basic rules. Examples are what we will use mostly is the L2 norm, which is the product of the sum of the components of the vector squared uh, to the power half. So this is like the distance norm. So these components are say displacement. So you have displacement component squared, summed, and then half. Or more general LP norm, where you don't square it, you raise it to the power p, and then you have 1 by p here. And then you can think about this a little bit as p tends to infinity. We have the L infinity norm, which turns out to be the maximum of the mod of the components of the vector. So maximum of xi among the 1 to n, I1 to n, the maximum of, and x1, which is for p equal to 1, is simply mod of xi. So sum of the mod of xi. So sum of all the components of the vector. So these are all legitimate norms. These are all legitimate operations that give rise to a scalar quantity that is indicative of the size of a vector, the quantity of a vector. So this are legitimate norms because they follow they obey these three basic rules. But they are very different in spirit, and under different circumstances we will have to use different kinds of norms. Many a time we will use this L2 norm, and the idea of a norm is very intimately related to the idea of uh, inner product that we also define for a vector space between two vectors in that space. So inner product of xy, inner product of xy is a scalar product that x is taken from the vector space, y is taken from the vector space, and the inner product gives me a scalar. And it also satisfies certain basic rules. One is symmetry. Inner product doesn't worry about the order. Is linearity. If you multiply one, if you take a linear combination of two vectors and multiply by z, then it is alpha xz and beta yz. So our definiteness, x comma x, the inner product of a vector with itself will be uh, will will be generally greater than 0 unless x itself is 0. And again, the choice of an inner product is not unique, but once you have decided on the norm, then your choice of inner product somewhat gets limited, because the inner product of a vector with itself, so if you have defined the inner product xy, and the inner product of, then by the same definition, inner product of xx should be related to the norm that you have chosen. So xx should give you the norm of the vector, and most often we use the Eulerian scalar product, which is like the dot product. So xy2 is the Eulerian scalar product. This 2 indicates the Eulerian scalar product, and we define it as x1 y1 x2 plus x2 y2 plus x3 y3 to xn yn. And then obviously if you use this to get the norm, then x2 square is the inner product of x with x according to this inner product definition. So this inner product definition, the Euclidean inner product, generates the L2 norm. It generates the L2 norm. Some other inner product may generate the L infinity norm or the L1 norm. But in our case, most of the time, we will use this as our inner product definition, so that the L2 norm is an outcome of this definition, or vice versa. The L2 norm actually indicates that this is our inner product definition. So given this is all for a vector, now having defined an inner product and a norm for a vector, the way of measuring the length of a vector, let's say, we after having defined that, let's get on to a matrix. So the matrix norm, the general definition of a matrix norm is max of norm of ax, which is a vector. Remember, we have already defined a vector norm. So this is a vector, norm of a vector divided by the norm of x, where norm of x is not equal to 0. Now remember, norm of x is equal to 0 if x is all 0, all components of x are 0, otherwise not. So in general, norm of x will not be 0, and the maximum of this is the norm of a. What it means is that this vector is a measure of how much x has been amplified by a. It is a measure of how much x has been amplified by a. If this is the length norm, L2 norm, then this tells you how much has the length increased or decreased because x is multiplied by a. So the ratio of this gives the amplification factor, gives the amplification in length, and then the max of that identifies the direction in which this has been amplified the most. So multiplication by a amplifies the vector x, and the max of that identifies the direction in which the amplification is the maximum. That's what the norm of a matrix means. In general, it also has some rules. In particular, if we have a norm for a matrix, we should be able to define a natural matrix norm, or an identity matrix of an the norm of an identity matrix should be equal to 1. Norm of an identity matrix should be equal to 1. So for the vector space kn cross n in which A lives, the identity is this. This is the identity matrix, and this identity matrix should have a norm equal to 1. So again, the norm of a matrix will depend on the norm that you choose for the vector. If you choose an L2 norm for the vector, so this is well defined, this is also well defined, and then the norm that is created by an L2 norm of a vector, norm of a matrix that is created by the L2 norm of a vector, is actually the maximum of its eigenvalues. If its eigenvalues are lambda, then the maximum eigenvalue among them constitutes the L2 norm of a matrix A. Note that it is not this. Remember, the norm of x, L2 norm of x, is summation of x I square. This is the L2 norm of x. In analogy, this we could have thought is summation of all the components squared to the power half, all the components of the matrix squared to the power half, with j and k going from 1 to n. But this is not the case, because if this were the case and I took the identity for which only the diagonals are 1 and everything else is 0, then I2 would have been root n, which is not correct, because I2 will have to be 1. We will, if we use this norm, note that for I, which has eigenvalues all 1, this is equal to 1 according to this norm. So the correct norm that is generated by this norm for vectors, correct norm for A that is generated by the L2 norm for x, is actually the maximum of the eigenvalues of A. So that gives me the L2 norm. So the measure of A is its maximum eigenvalue. The measure of the vector x is its length, its Euclidean length, so to say. Okay, so this is how we define a scalar norm corresponding to a vector or a matrix, square matrix. Given this definition, we can state this perturbation theorem for a linear system without proof. So if A is an invertible matrix, so I have a system Ax equal to B, A is invertible, and the mistake, the deviation in A, perturbation in A, the norm of that, remember the norm of that is the maximum eigenvalue of delta A, let's say 2 norm, is less than one by the norm of A inverse. Okay, then this matrix, the perturb matrix, is also invertible, and this is the relation that we should be looking for. This is the relation that will be satisfied. So this is the norm of delta x, the error in x, divided by the norm of x. Both of these are scalars, so you can divide them. So this is actually, according to our definition, remember, this is xj whole square summation over j, and then to power half. This is the L2 norm of this. This is the L2 norm of this is also similarly calculated. So this is the relative error of the norms. This has to be less than the condition number of A by condition number of A delta A times norm of delta A times norm of A, and then this is the error, relative error in the norms of B that you have committed. This is the relative error in the norms of A that you have committed, and these things together will have to be greater than the error in x that occurs, where the condition number of A is again a scalar. Condition number of A is the norm of A multiplied by the norm of A inverse. Condition number of A is simply the norm of A multiplied by the norm of A inverse, and when we use the L2 norm, remember that the norm of A is actually the maximum eigenvalue of A, maximum eigenvalue of A. So this would be the maximum eigenvalue of A. When you take the norm of A inverse, you will get the maximum eigenvalue of A inverse would be the minimum eigenvalue of A. Therefore, the condition number of A in case of the L2 norm, if we use the L2 norm, is simply lambda max by lambda min. So with this, the condition number of matrix governs the amount of error that is caused given the amounts of error that are incurred in the right hand side B vector or in the matrix A matrix. Okay, so the condition number is a ratio of the maximum and the minimum eigenvalues, and this relation actually allows us to measure how much the errors are going to be. So for a matrix, for the stiffness matrix, let's say the condition number is of the order of 10 to the power s, and we make relative errors in A, that means norm of delta A by A and norm of delta B by B are both of the order of 10 to the power minus k, small number, k is a positive number. So then the relative error in the solution will be of the order of 10 to the power s minus k. So if the condition number is large, then the error will be large as well. So you can make a small error here, but the error in x will be large if the condition number of the matrix is large. So that is the basic result, that we have to look at the condition number of the stiffness matrix in order to determine how stable the solution is. An unstable, a very large condition number can potentially lead to an unstable solution for the degrees of freedom. Even when A is non-singular, even then there might be a large error in X if you commit a small error in, let's say, B. Okay, so this is the result that I wanted to highlight, and this is a result that you must keep in mind. The key takeaway is the ratio of the eigenvalues of A, which defines the condition number according to the L2 norm, which is what we are using. You should also remember the definition of L2, the L2 norm for a vector, the L2 norm for a matrix, both of which are connected to the idea of inner product, which implies that right. So this is what I wanted to say about the stability of this matrix system. And now in the next class we will look at some iterative methods, typically the conjugate gradient method, which has become quite popular of late.